Bismillahirrahmanirrahim. My name is Tahreem and my topic of presentation is IR spectroscopy, which is abbreviated form of infrared spectroscopy. So first of all, I'll explain the basic definition of IR or infrared spectroscopy. Infrared spectroscopy is the analysis of infrared light interacting with the molecule. Means we analyze the uh, interaction of infrared light on a molecule. That what are the effects? This can be analyzed in three ways: by measuring absorption, by emission, and by reflection. There are three ways to analyze that interaction. So the main function of IR spectroscopy in organic and inorganic chemistry is very vast because it is used to determine the functional groups in molecules. IR spectroscopy measures the vibrations of atoms, and based on this, it is possible to determine the functional groups. So we can determine the use and its effects on organic and inorganic chemistry. The basic principle of IR spectroscopy utilizes the concept that molecules tend to absorb specific frequencies of light that are characteristic of the corresponding structure of molecules. Means they do not absorb all frequencies of light. There are some specific frequencies which they absorb. The energies are variant on the shape of molecular surface, the associated vibronic coupling, and the mass corresponding to the atom. For instance, the molecule can absorb the energy contained in the incident light, and the result is a faster rotation or a more pronounced vibration. So this is the basic principle on which IR spectroscopy works. I'll explain IR spectroscopy instrumentation and interpretation of spectra. Means how to draw a graph of IR spectroscopy. The instrumentation of infrared spectroscopy is that first of all, a beam of IR light from the source is split into two and passed through the reference and the sample. Now both of these beams are reflected to pass through a splitter and then through a detector. Finally, the required reading is printed out after the processor deciphers the data passed through the detector respectively, and the reading is drawn on a graph and the graph is interpreted. So here is a diagrammatic view of IR instrumentation. There is an IR source, this is reference, this is sample, and it is in a monochromatic system. Here is splitter, and this is the detector. After detecting, the graph is plotted and it is read out here. So there are few steps that how can we make our IR spectra better and the successful IR spectra interpretation. Step number one is always interpret quality spectra. Means you should interpret a spectra. Can you can take the readings again and again, but the quality should be best. And step number two is avoid mixtures if possible. Means the samples should not be the mixtures. Step number three, use other knowledge of the sample. Means you can get other knowledge and then you can enhance the quality of your spectra. Here I explain few examples, few spectrums of organic compounds. And first of all, I'll explain an alcohol, the infrared spectrum of an alcohol, ethanol. So this is the graph of IR spectrum of ethanol, CH3, CH2OH. It looks like this, and I'll explain the IR spectrum of ethanol, that the OH bond in alcohol absorbs at a higher wave number than it does in an acid. So It's somewhere between 30 to 130 to 3550 per centimeter. In fact, this absorption would be at higher numbers still if the alcohol isn't hydrogen bonded. For example, in the gas state, all the infrared spectra on this page are from liquid, so that possibility will never apply. Notice the absorption due to the CH bond just under 3000 centimeter, and also the trough between 1000 and 1100 per centimeter, one of which will be due to the CO bonds. So here is the graph of ethanol. There is another example, the infrared spectrum for an ester, ethyl ethanoate. This time OH absorption is missing completely. Don't confuse it with the CH trough, fractionally less than 3000 per centimeter. The presence of C double bond O is seen at about 1740 per centimeter. The CF single bond is the absorption at about 1240 centimeter. Whether or not you could pick that out would depend on the detail given by the table of data which you get in your exam, because CO single bonds vary anywhere between 100 and 1300 centimeter, depending on what sort of compound that they are in. Some tables of data find it down so they will tell you that an absorption from 1230 to 1250 is the CO bond in an ethanoate. So the graph of ethanoate looks like this, and you can see the absorption is very different from ethanol. There is another example of a ketone, the infrared spectrum of a ketone, propanone. This is similar to infrared spectrum for ethyl ethanoate and ester. Again, there is no trough due to the OH bond, and again there is a marked absorption at about 700 centimeter due to the C double bond O. Confusingly, there are also absorptions which look like that as if they might be due to CO single bond, which of course aren't present in propanone. This reinforces the care you have to take in trying to identify any absorption in the fingerprint region. Aldehydes will have similar infrared spectra to ketones. So, if you want to draw the spectra of aldehydes, you can also draw, because it's very similar. And there are a few steps you should keep in your mind while drawing the spectra. So your quality of your spectra should be maintained, and the spectra of infrared spectra of propanone looks like this, and you can see it's similar to the spectra of this. So here I explain few examples, and I'll explain the IR spectroscopy, how to draw the spectra, and that's all from my side. I hope I explained my topic on my side, and all the confusion should be gone.